Good morning. So, we will continue our weak formulation. Last class we have studied the solvability of L naught of u equal to f. What is L naught? L naught is the operator, elliptic operator without the lower order term, and that too in conservation D form. Okay, Aij of x dj. This is your operator L, and with the Dirichlet boundary condition, this is what we have done. And then you proved this transformed into this form AUV equal to FV, where you are looking for u in H1 naught. This we have already done, and this happens this equality for all V in V in H1 naught. And then you prove that there exists a unique solution u in H1 naught, and which also satisfies the regularity, the estimate u in H1 naught is less than or equal to constant norm in f in L2 of omega. Okay. And this is what we have done. In particular, you can apply for that. So, let me to make you familiar. In particular, if L naught is equal to minus Laplacian, then you have this problem, the minus Laplacian u equal to f in omega and u equal to 0. So, this is a particular case on d omega, and its weak formulation is and because this is the operator we will be studying again and again, and hence I am writing it once more. Formulation is integral of grade u grade v equal to integral of f v for all v in v. No, sorry, not for all in v in v, for all v in H1 naught, and you are looking for a solution u in H1 naught. So, this has a unique solution u in H1 naught such that norm of u at thing is. But just I want to recall, which I have presented once again. So, how do you get back? So, this is called this is the strong form, this is the weak form. So, if u is classical, this you should always check it. Whenever you create a weak formulation, the classical solution should be a weak solution, and if there is a weak solution and the width and the u satisfies the regularity, additional regularity or smoothness, and then you also should get back your equation, then only you can say that your weak formulation is a good weak formulation corresponding to your PDE. So, if u is classical implies that is u satisfies 1 implies u is weak, is a weak solution. This I remarked, but that is important. Conversely, so assume, so let us see, this is what you have to assume 2, that means that u is a weak solution, and you assume the some regularity, you can assume C2 of omega bar, but it is enough to even to assume. So, you start with u is in H2 of omega, this is an additional smoothness, then that implies then this 2 can be can be integrated by parts. Again you can apply integration by parts to get it, integral of minus Laplacian of u f over v is equal to 0. If u is in H2, this will become an L2 function, you see, and this is true for all v in H1 naught of omega. In particular, this also implies this minus Laplacian of u f. If you assume f is in L2, this is whole thing is in L2, and hence this is true for all v in particular this is true for all v in d omega, because d omega is a subspace of H1 of omega, and since d omega is also dense in L2 and this equality is also true in L2 sense. So, you get for all V in L2, this is an important thing. Therefore, this equation is true in L2 sense, that implies minus Laplacian of u equal to f. First you get this is in distribution, that is the meaning of that. This is also you get minus Laplacian of u equal to f in L2. So, to understand various meaning, minus Laplacian of u plus f in L2 means for all test functions the value is 0, but this is L2, the L2 integral is 0. Since this is L2, u implies minus Laplacian u of u plus f is in almost everywhere. Further, if u is in C2 of omega bar, you get then this and f is in C omega, and so let me go. Okay. So, what is it? Let me read once more, write it. Further, these things you have to check it all the time. Further, if u is in C2 of omega bar and f is in C omega, implies minus Laplacian of u minus f equal to 0 point wise, you see, point wise, and u equal to 0 on d omega point wise, implies u is classical. So, this is what trying to say, that you have to prove. So, whenever you give a weak formulation, not only that you have to check that u is classical, that implies u is weak, you also have to check the converse part of it. If u is weak and u satisfies the smoothness condition, then you can get back your equation as well as the boundary condition, depending on the amount of smoothness available to it. And here also you will get your u in H1 of omega or H1 naught of omega less than or equal to constant into norm f in L2. One more last remark regarding these things. In fact, you can, it's in fact it is enough to take f is in h minus 1 of omega. Okay. In this case, integral f v to be replaced by f v, which is a duality bracket. This v is in h1 naught and this is in h minus 1 of omega. So, we may normally write this also this way, but you have to be take it with a pinch of salt, in the sense that if f is in h minus 1 of omega, this is the meaning of it, and you can have the same Lax-Milgram lemma, and this is also true for your L naught operator. Okay, there is no difference. So, this you will get it as constant into norm f in h minus 1 of omega. You see, you get that. Now, with this we will go to the inhomogeneous situation, non-homogeneous case. We will do quickly that non-homogeneous case. So, what is your equation? You have minus Laplacian of u equal to f in omega and u equal to g on d omega, you see. Now, you cannot work with h1 of omega immediately. So, what do? You recall trace theorem, So, it is important to understand now trace theorem which you have studied last the part 1 of this course, as well as we recall in this course as well. And what is a Rees theorem? So before that, let me tell you. So if you are looking for solution, if we look for u in h1 naught of omega, h1 of omega, you cannot look u in h1 naught of omega. If u is h1 of omega, then you restrict by trace theorem, you restricted to d omega is in h half of d omega. So you see, you know that. So we need to assume, this forces to assume, we need to assume g, which is the boundary value in h half of gamma or d omega, and f for f we assume either it is in L2 or in h minus 1 of omega. You see. Now by trace theorem, trace implies, so you have to solve this problem with these two assumptions, g in h half and f is in L2 of omega. So trace implies there exists u tilde, that means you have a mapping from h1 of omega to L2, gamma naught trace u tilde in h1 of omega, such that, so you are first looking for a function which is has the trace value u tilde restricted to d omega is equal to g, and you will also get an estimate such that norm of u tilde in h1 of omega less than or equal to norm of g in h half. So such kind of thing, these are all part of your trace theorem. So you can choose such a function. So what you are looking for, so what you have to do is that, so you have a function already u tilde, so what you are looking for a set, so you are looking for not in h1 of omega, so h1 naught of omega, so you are looking for a solution v in h1 of omega such that your v minus u tilde is in h1 naught of omega, because you, that means your u tilde has the trace value g, and hence v also has the trace value. So looking for the cases set, basically you are looking for the boundary values g. So this is a closed convex set, closed convex set. Okay. So this is a small exercise which you can do it, exercise. So you verify that one. So now I can look for a solution. So so what is the weak formulation? You derive the weak. So I am going to leave so many exercises because it's basically an application of integration by parts. Take a test function and you there, and then integrate by parts. So what is the weak formulation? So I call this to be 1 formulation. So do this as a small exercise, all that you derive. I do not want to keep on deriving. So you are looking for a u in k, but your grade u and grade v is equal to integral of f v, if f is otherwise the duality omega, and this happen for all v in h1 naught of omega. Of course, you cannot apply the Lax-Milgram directly because the spaces which we are considering are different. Stambakia, you can't do that immediately, but this is a weak formulation. So prove that this is is indeed a genuine weak formulation. Okay. So the exercise is 1 implies 2, means if u is a weak solution, strong solution, satisfies one point wise, then you can get a u is a weak solution, and 2, that means you have a weak solution plus your u plus the smoothness, smooth implies These are all trivial, exactly what we have done. Sometimes it is not trivial, you can see when you study here the Stokes equation etc., things will not be that trivial. Okay, so you may have the difficulty. The problem is that immediately you can't apply the Lax-Milgram lemma. So how do you solve it? Now proof of existence uniqueness. Okay, existence uniqueness and continuity estimate. Continuity. What do you look for? The step is again in 2 steps. We will do it in thing. This is a small trick. Look for, because you already got the boundary condition G. So you look for your U is of the form U tilde plus W. Okay, and then 2 can be written as, now U tilde is known, integral of, so find W. So you want W in now in H1 naught, because U tilde already satisfies your boundary condition. So W should be satisfying the 0 boundary condition, such that you are you apply the 2 you are applying it is, you can first apply grade W, grade V, this is over omega, and this is equal to integral of Phi, which is for all V in H1 naught of omega, and then you will have your minus by integral of grade U tilde grade V, because U tilde is known is the thing, and this is for all V in H1 naught. Now you see this together is a linear form, non-linear form. So again you can apply Lax-Milgram, to get W in H1 naught, and the W now can be estimated as norm of W in H1 naught is less than or equal to constant into norm of F in L2 plus norm of gradient of U tilde in L2. Okay. Of course, if F is in H minus 1, it will be H minus 1, and but gradient of U tilde is less than or equal to G in H half. So you see, so and you and this is norm in F tilde plus norm in H half. Of course, the to get unique W in, but this does not imply uniqueness of U. Given U tilde, because does not imply uniqueness of U, because W is unique for a given U tilde, but the U tilde there will be many U tildes. So uniqueness is trivial, however, uniqueness, if this is you take it, so you take U 2 solutions U1 and U2 solutions, then U equal to U1 minus V2 is also a solution. You can see that the 0 solution satisfies, this is easy now, satisfies minus Laplacian U1 equal to, this is in H1 naught, you can see that, and you get integral of grade U, grade V, because it is the same F, it satisfies the same F, you get your omega, this is equal to 0 for all V in H1 naught. That is a standard way of proving uniqueness, and take V equal to U, implies grade U square equal to 0 omega, that implies U equal to 0 almost U equal to constant. okay, and that implies in the sense of since u is in H1 naught, the boundary values are 0. So, you have basically u equal to 0, everything in the sense of trees. So, you have the uniqueness for a non-homogeneous problem, and you also have this estimate, that is more important. This is also, this is a continuity estimate. So, you see, so you have your continuity estimate. But try to work it out in and such a concept proving the when you are have a PDE and whatever form you give it when you are proving existence, give a formulation and prove existence, uniqueness and regularity is called the well-posedness of the problem. Well-posedness of the problem, and this is called Hadamard well-posedness. Okay. Now, some few immediate things you can do. You can consider slightly more general immediately. For example, can consider L naught of u. You can add a first order term, but then there is some problem equal to f in omega with u equal to 0 on d omega, and the assumption is of course a naught we assume L infinity, and we also assume a naught of x non negative. So, the exercise is that trivial, give weak formulation. So, no problem, you can add one more term and give weak formulation, and I said I am just taking prove the equivalence in the sense that strong solution is a weak solution and weak solution together with the thing is a strong solution. You should always do that even if it is trivial. Prove the equivalence, that is what I meant by equivalence. Otherwise, weak solution need not be a strong solution, and then estimate existence, uniqueness and estimate. Okay. Well-posedness, prove the well-posedness means existence, uniqueness and that is trivial. Okay. And if so, because what you can do is that is actually you can get this operator L naught plus A naught is elliptic, you can prove that. That is what you want to prove it. You give a weak formulation and that. Of course, L naught ellipticity is given, but the weak formulation corresponding to this one you have to prove that it is elliptic. That is what it is. If Aij is symmetric, Aij is symmetric, this also you know, then solution is characterized by, then U is characterized by, as we have seen etc. U in H1 naught and Ju equal to minimum of Jv V in H1 naught. And what is your Jv? Jv is equal to half of Aij dV by dxj dV by dxi. Exactly you will get one more term, integral of half of A naught of x V square minus integral of Fv. This is for all V in H1 naught of omega. But when you, I will have some interesting remarks later. So, we want to general case in divergence form. we do not even assume that A naught is non-negative now. So, what is your operator? L of u is equal to minus di of aij of x dj of u plus the summation is there all the time. I am telling ai of x gi of u plus a naught of u x u equal to f with u equal to 0 on the boundary. So, this is your L. Okay, this is in omega. So, how do you can still give the weak formulation. So, you assume of course Aij, assume conditions on Aij as usual, boundedness and ellipticity, conditions on Aij. I do not keep on repeating, okay, as above, and you also assume if you want Ai to be say C1 of omega bar, A naught is in is C omega bar, all that. You may not require such strong thing, maybe it is enough L infinity, all that assumption you may not require. So, you will be using L infinity conditions. So, I want to give a weak formulation. So, derive the weak formulation. So, I will leave it to you. These are all small exercises. In the process of its exercise, not that non-trivial exercises, is an exercise to learn your subject. Anyway, you have to read and read what I write. So, it is better that you do it weak formulation. Weak formulation is find u in again H1 naught such that your AUV is equal to FE. You can write down FE, FE can write either this form or integral form depending on where it is available. But what is your AUV? AUV in this case integral of Aij of x dj of v u di of v plus integral of ai of x di of u v plus integral of a naught of x u v. This is what your AUV. Okay. The problem is that even if we assume, even if this L naught Aij is elliptic, A need not be elliptic. A need not be H1 naught elliptic. Okay. That is what in this something a particular case I told you just now. You see, in this case when you add a non-negative term here, first order term, you get ellipticity. But in this case we are not even assuming that. Okay. I have something to do, but AI does not, but still A naught is the troubling term for getting existence. Okay. So, we will see that. Okay. So, A need not be elliptic. Okay. We already mentioned that A need not be. But in some cases, if A is elliptic, then that implies there exists unique solution by Lax-Milgram. This you can see. Okay. Assume that A is elliptic and then show that there exists a unique solution satisfying the estimate, satisfying the standard estimate, satisfying the similar estimate. Okay. Well-posedness basically, This is an exercise, you can do that. Trivial, you are just verifying ellipticity is given, so basically there is nothing to do that. Now the problem, actually you are going to state a general theorem, probably maybe I will just state the theorem. So this is basically an application of Frdholm alternative. We are going to do, we already seen the Frdholm alternative in the Babuska thing, Frdholm alternative. So let me state the theorem. Okay. So let me, I have to write before that, right? How do you do to understand the solvability? So again on the side, let me recall. So this is about the compact operator, right, which we have applied operator. So if you want to solve your equation Tx minus lambda x equal to f, you have to understand the equation, the solvability of the homogeneous equation T star of x minus T star of y minus lambda y equal to 0. And what is this compact operator theory? It tells you that even though you are working in an infinite dimensional space, this is a finite dimensional. Kernel of T star minus lambda I is finite. That means the homogeneous equation is finite dimensional, and then the solvability of this one, that this f has to be in the orthogonal complement of the kernel space. This is what we have applied, and this is precisely your finite dimensional situation regarding the solvability of Ax equal to b. If A is invertible, then it is uniquely solvable. If A is not invertible, you have to have this be in the range of the A star kernel of that one. That is what you will be doing it. So this we will do this application, and for the general equation we put it in this form, and you state the results. Since the time is up, I will continue this theorem and give the proof of that, because it is a beautiful application of again Frdholm alternative. The things, one of the important thing you study in functional analysis. Thank you very much.